Thank you. So let me then begin stating a theorem. And I will then state the same theorem I stated on Monday, but it's much nicer now. I will only assume that it's a hypercube, so the statement is not so awkward. But just so you remember what is a main theme. So let then here epsilon and r dn be given. So then the following star below holds for any b. So I will look at hypercubes of any, this will be the size, goes from b to minus b, and any variety x, a closed geometrical integral of the dimension r and degree d. So it's an absolutely uniform statement which should be true, I mean, for all those varieties. And the statement what holds then is the following. So if now we have a prime, in fact it could doesn't have to be a prime. It's just then you have to define what do you mean by a non-singular point modulo n. But let's assume it's a prime. And then we will have this exponent here, which looks ugly, but we will see in a moment that it's quite natural. So I call this Heath-Brown exponent because in the case of hypersurfaces, it's occurred already in his papers in Annals of Mathematics. If you have this, and if you take then here a non-singular non-singular point modulo p, so again I just take the scheme theoretical closure to get the model of Z, and then I reduce modulo p, and then I have a class here, and this if this and this is non-singular, then is a hypersurface Z modulo Pn of degree. So this degree is bounded from above. It depends only on dn and epsilon. So it doesn't matter what kind of Hilbert polynomial you have, what kind of equations you have. So the only thing which are fixed are these parameters here. So this degree of this new variety is then depends only on that. So it's not Serre's twisted sheaf here, it's analytic number theory, the big O of analytic number theory here. So such that if you count all points, integral points, and on this model corresponding to sex, and you look at those in this box and which reduce to y, then they all lie in Z, while here x itself does not lie on Z. So I got some questions about, well, how do you use this? I mean, you could just imagine that as a first approximation you have a smooth variety and that it has good reduction everywhere. Because in the general case, it's not harder at all. So if you can understand this case, I mean, then the other difficulties with singular points are easily handled here. So in that case, then you just sum over all residue classes. So you get an O of Pn residue classes by trivial estimates for Fp points on a variety of dimension R. So this means that this exponent will disappear. So this means that if you want to count a full set inside the box, it will be covered by that many hypersurfaces. And since this hypersurface does not contain X, it means that you can reduce the original counting problem to a problem in lower dimension. And this was exactly how Heath-Brown proceeded when he got, say, had results for surfaces of degree D, and then he reduced it to problems for curves of degree D. And he then covered them by that many curves. So, and then, of course, there are some extra complications when you have singular because here I've stated for nothing, but those problems are very, very minor compared to understanding this and how to use it in a clever way. So just think about the case of good reduction everywhere, and if you want to understand how it is used. So now what I want to do is that I want to give some kind of complete proof of this. So I have before discussed the case of when you have unequal sides, and then you just combine, add this stuff I've talked about the other days. But just so you see the whole picture, so what remains basically is then only to study this p factor, which I started with last time. So let me now start with the complete proof. So let then here S then, S of k, be the homogeneous coordinate ring, homogeneous coordinate ring of x, and then I will then introduce this Hilbert function here. In a moment I will replace this by in quarter or so by A0 x of the assessed twisted sheaf. I take the global sections. In principle, it's the same thing. For k sufficiently large, it's always the same thing. But for the moment, I do it in the most concrete way here. Because I would like to show some refinement on this, some p-adic refinements, and then I will use global geometry. I mean, I will use the volume functions, and I will use stuff in Lazarsfeld's book and so on. But here, to prove this, you don't need much global geometry of x. So I will, after I've proven this, I will give you a refinement where you use much more of the global geometry. So what we will do is then that we will show that. So we will form this determinant. I mean, it's not by random, it's called the determinant method. We will show that there exists some k of n, which is then depending only on dn and epsilon, such that the following determinant is 0, such that determinant m is equal to 0. So then I form the usual determinant for then m. So I have then a number of polynomials, f1, f1, phk. So this will be what I call, I had other notations before, but maybe it's nicer now because I will focus now on the p-adic aspects. I don't really need that they're monomials, so therefore I switch notation. But I will apply this to the monomials we had before when I looked at the Archimedean and when I give the upper bound. But to give the upper bound is trivial now. So everything I said Monday, Tuesday, Wednesday becomes trivial in this case. I mean, you don't need to know you don't need to read Mumford's book in geometric invariant theory to estimate the determinant. It's completely trivial if you have a box where all sides are equal. So I want to focus on these p-divisibility aspects. And it turns out that this is even more subtle geometrically. You need to use a minimal model program if you want to have the best results, for instance. It's strange when you just see a determinant, you don't think it's very deep, but it's not just linear algebra. So the name is somewhat misleading. So for any monomials, f1 up to then here fhk of then degree k in x0, xn, and any points and any points p1 up to phk belonging then to x. So let me write then z, and now I just write 1b because I mean we are in a cube now. So this will now imply the assertion. So this will imply the assertion. You can think as follows. You just take the Veronese embedding by degree h of k, and then you know whatever hk point you take, they lie in your linear space. And this means that hyperplane. So this means that they must all lie in hyperplane. So this means then that we have a new equation which is unsatisfied for all those. So this is what I will do. So I will prove now that this determinant is 0. And I have already done a lot of the work, so I just want to conclude so you see the all aspects here. Oh. So that was a bad surprise. I mean, okay, I should have. Yeah. What shall I do? Yeah. Yeah, I have to do this. The other spacing. Okay. So I will be able to read. I have problems, but maybe I'm old and I don't see well. I had problems myself to see on the blackboard. I mean, the first day. So this is one. So there are two aspects. You have to prove that it's bounded, which is trivial, and you have to found the p-adic, found the p power factor. It's easy to find one high p factor with the p-adic implicit function theorem. If you want to find the best p factor, then it's another matter. Then it's quite deep. But the improvements you can make are not enormous. So this easy argument I will give gives you basically the best result in many cases. And when it doesn't give the result, it's almost as good as the best result. So there are now here two steps. So there are first now here step 1. This is now then here that this determinant of m is of course smaller than hk faculty times b. I mean, each term here is bk, and if I take the product, say, on the main diagonal, I have hk. So this you get immediately. So this is trivial. So this is trivial if, say, f1, fh are monomials. So I will apply this to monomials. And of course, I will choose a monomial basis. Why do I want the basis? Well, I want this condition. So I want that this condition should be fulfilled. So then I have to choose some monomial basis. Then it will be automatically fulfilled, this condition. And then it is a step further than here. What I will need is I will need that h of k is equal to, I've used results from on the Hilbert function, so I will need information about that. When I compare this upper estimate with the p factor, so then this will be dk r plus 1 divided by r faculty plus o, an error term, d of n and k of r. So what happens here is I assume that it's integral. In particular, it's reduced. So then it's known that there are only finitely many possible Hilbert polynomials of degree corresponding to d and r and n. So the only finitely many Hilbert polynomials, and it's well known then we can estimate them in this way, and it will be then uniform since we have only finitely many Hilbert polynomials. So this is kind of standard knowledge of Hilbert polynomials, so by the theory of Hilbert polynomials. So the new thing then I want to discuss today, I started briefly last time, is then to find p-adic factor then. So step 2. And then what will happen is then I will look at the local ring of a closed point on X, and then I will count the dimension of there's a filtration of the local ring, and then you will get a lot of binomial coefficients. So let me then introduce them, and you will see in a moment why they occur. So the statement first is a bit awkward because there are many binomial coefficients, but it will be very easily seen why they occur in a moment if you just have some patience. So suppose here that I choose then J such that this sequence will grow, so there is some J for which this should be true. And let then here, so I introduce a variety here, J of K. And this variety here is a kind of weighted sum of binomial coefficients. So I have then goes from Y to K. And then I have here R plus I minus 1 over I. So plus times I plus, then I take the remaining ones, HK. You will see in a moment why this occurs. So let me just give the statement only numerically here. So times then here J plus 1 here. So if that is true, then I will have that P of J of K will divide the determinant of M. So then what I will do, I will give a much more nicer expression. I will give an asymptotic behavior of this P exponent, just as I gave of the B exponent in a moment. But I first want to prove this, and then we use it in a clever manner so we don't have to deal with all these binomial coefficients here. So I already started the proof last time. So in fact, it's quite easy. So we reduced last time. We reduced last time to the following assertion. And this was then after, first I dehomogenized, after dehomogenization, yeah, I hope it's, and using the p-adic implicit function theorem, using implicit p-adic function theorem. So after using that, I got a much cleaner statement for a much nicer determinant. And the new statement then I got was the following. So the following lemma is enough to get this statement here. So then suppose we have then formal power series in our parameters f1 times f of h of r. So what I first assumed was that I could assume that x0 was not divisible by p because it has to be non-zeros at modulo p. It has to be non-zero somewhere, and I can just make a permutation, and then I just introduced affine coordinates. So then I got some affine polynomials instead, and then I just use implicit function theorem to express them as formal power series, and so they will now lie in following ring of R, because the dimension is R, so I can express everything as formal power series, I of R. And that then I have p-adic points. So then this can be P, which I had, could then be viewed as p-adic point on this variety here. So I have then here A of n times set of P. With then, which are, they first lie in a subvariety, but everything I will use is that they will be congruent to 0 modulo P. So I will not use here that they lie on the variety, which are congruent. I already used this, exploited that when I expressed them as formal power series here. So, which are congruent to 0 modulo P. Then P of J of K divides this determinant of f of 1 or p of 1 up to the last one, f h k p of h of k, etc. So you have f1 p h of k. So I think I don't have to write it. It's a square matrix here. Then p, yeah, maybe I write divides. Divides. So I explained last time really. So it was just these two steps. So now how do you then do this? Well, when you count a determinant, you have the right to use elementary transformations. So we just look at linear combinations of f1 and f2, etc. So it's very easy. So proof. We may after elementary transformations, transformations on in this f1 up to fhk, assume over set p. Then I may assume that. So imagine I have one here which has a formal power which has a constant term. Then I can just subtract multiples of that such that the other ones do not have a constant term. And after that, I try to eliminate the linear terms, and then I eliminate the quadratic terms in it as far as possible. So this is how it goes, and this can be stated such that we may also assume that the following, that all but r minus 1, this is 1, at most 1 has no constant term, and then I eliminate the linear terms, and then I get this bit, and then I eliminate the quadratic terms, etc. R plus 1 over 2. And finally then that all but r plus j minus 1 over j. And if you look at the sum, it's actually, I think, binomial coefficients as well. That all by those fi's then are in. I look at the multiple of this ideal at 0, defining 0, j plus 1. So as long as this expression is smaller than h of k, I can continue to eliminate the terms of lowest degree as long as this r plus j over j is smaller than h of k. So now this implies the assertion. This implies the assertion as you do now have that P1 is congruent to P2, was incongruent to P, h of k is congruent to 0 modulo P here in this set P n. So you just plug in these values, and then you see that this factor here. So now we have both an upper bound, and we have now a large p factor. And now I just want to replace this by cleaner expressions, and then I will compare these two terms, the b power and the p power. And then you will see that this funny exponent will appear. So I think now then I can erase, all proof here. So now I will make some heuristic comparisons. I mean, it's very easy to treat, I mean, all the error terms, I mean, this O. So, I mean, it just takes time, it's tiring, but it's not hard at all. So I will not give a complete proof, but I will give some heuristics, which I think will convince you. So first then, just as I noted that you could, this exponent, I gave you, replaced it by a cleaner expression there. I will do the same thing for this. So remark. And of course, when you have a sum, the standard method to see the asymptotic behavior here is to compare it with an integral. And this is absolutely elementary mathematics, so I will just state the end result. So by comparing then the sum, defining then here j of k with an integral, then one sees, and this is EC, that you have that this j of k is had the following asymptotic behavior, d 1 plus 1 over r, and you have then here k r plus 1, and you have then here divided by r minus 1 faculty times r plus 1. And then you have an error term here, and this error term will only depend on d and n and this k of error. So this is no advanced mathematics, it's just this numerics here, you sum, you show that it has this asymptotic behavior. So now I just then, I should say here to get this, I use a fact because this is formed, this is a sum with hk terms. So I should say here that we use here, of course, again, that khk is equal to what I wrote before, d kr plus 1 divided by r faculty plus O over k of r. Okay, so it's not interesting to give all details here. It's easy, it's elementary. So I have this, and I have this. So now I then want to convince you that you get this exponent. So heuristics. The condition then here. So I have then here pj of k should be bigger than b k h of k. So this is a Hilbert polynomial, and this had to do with this expansion as a p-adic series here. So why do I consider this? Because in fact, I do have this faculty here in the determinant as well, but this constant is easily absorbed by b epsilon. And these error terms here, you can also absorb them if you just add this b epsilon factor here. So let me just say that this one here is roughly equivalent to. So then it means that you have to compare that with p d 1 plus 1 over r. So now I replace gk by this expression here, modulo then k r plus 1 divided by r minus 1 faculty r plus 1, that this should be bigger than b, and then I have then here d k r plus 1 divided by r faculty. Now these expressions have a lot of similarities. We have k r plus 1, we can cancel them, we can cancel r minus 1 faculty, and so on. So you see immediately that this simplifies. So this is equivalent to that p d1 over r divided by r plus 1 is bigger than B over 1 over R. Because I can get rid of, I can cancel this term, I can forget that, I can cancel this, and I can also then cancel 1D, I can also cancel 1D, and I can cancel R minus 1 faculty. So this is all that will survive, and that you will have then here that P is bigger than B, R plus 1 divided by D1 over R of R. So this is what I need in order to have, basically, in order to have a P factor which is bigger than this bound. And I have these error terms, but if I just arrange such that I include a factor B of epsilon, I will really be satisfied, and this will then force this determinant to be 0. So that would then complete the proof then of this theorem. In this case of these lopsided boxes, it's exactly the same. It's just to replace this trivial bound by these bounds I explained to you with this weight, Chow weight, etc. So now then I want to convince you that even the p-adic part is quite subtle. And what is amazing is that there was I talked about these improvements in 2006 at MSRI, and then some 8 years after, suddenly in Diophantine, and then I talked with Lazarsfeld. There was a geometric invariant, and no one could see any use of that. In 2014, suddenly it's used now in a generalization of Roth's theorem. You use exactly the same invariant. And recently in this Kähler-Einstein metrics, they also use this strange integral over volumes that no one thought would have any meaning. So again, there is a resonance between this determinant method and Diophantine approximation and theory of Kähler-Einstein metrics. The same kind of invariants appear naturally in all 3 theories. So I would like to tell you now a little bit about refinement. So what I will do is that I will replace this exponent there by some integral over volume. So it will be some geometric sophisticated than that invariant, which are nicer to see. The problem is that if you meet an analytic number series, you don't care about how beautiful the theory is, you just want to have the best bounds. And the improvements are on the order 0.0001 or so. So this is why I was not that motivated to publish this, because for cubic surfaces, in order to get the best bounds, I replace this exponent by this other more sophisticated exponent, which is used then of this volume function studied in Lazarsfeld's book. So now I want to tell you about the more sophisticated approach than just using the p-adic implicit function theorem, which leads to some small improvements of this exponent. So Manin conjectured in the 80s that if you take a non-singular cubic surface, if you look outside the lines, and you want to, then he conjectured that the gross order should be linear. But no one could even prove quadratic gross order until 15 years later. Heath-Brown did that. So the best result now is 12 over 7, so which I proved. And we'll use a refinement of that result. So. And this is quite typical for surfaces. All the best bounds are more or less obtained by the determinant method. Unless you have a very nice structure. I mean, if you have a toric surface or something, then of course you can exploit that structure. But if you have, so to say, an arbitrary surface by random, given by equation, I mean, the determinant method is in general the only tool you have. So the only other method would be sieve methods, but they give much worse result in general. So. Some really clever papers by Hooley using sieve methods, but still sieves are so general, so you don't take into account all the special features of the Diophantine problem. So even those very sophisticated papers of Hooley, you can obtain better results using the determinant method. So I would love to have other methods, but I mean, this is the only method I know, so therefore I talk about that. So the next theme is then here a refinement of the p power factor of determinant f of I, p of j, so nothing, well, of course, I have for the size of the determinant, I just have the same trivial bound. I can't do much about that in this case. This is, but I can improve this p factor. So in fact, then, this matrix M you see here, that M, M, the determinant of M, it depends only, so now I will use a little bit more sophisticated, but I think I frightened all the students here, so I mean, for the people here who are here, so they will not be very sophisticated with sheaves or so. But I will use a little bit more of sheaves now and less polynomials. So determinant of M depends only on the images of these F1. So I had these polynomials in this determinant of degree k. So I can, of course, view them as global sections of O of k. So these, I can view them as global sections of Pn of z in O of k. And then they only depend on the image here in this model over set of O of k. So I can just as well start with global sections here and try to evaluate that. So I will change notation then. So one may then consider arbitrary sections here. Determinant then Si of Pj for any global sections, and here S1 up to shk, then belonging to h0 of x tilde, and I have then here O x tilde of k. It doesn't need to be surjective at small k, but I mean it will be surjective if k is sufficiently large. It's just an exercise in Hartson's book. There is actually no change here, because this determinant method, it will only deal with when k is sufficiently big. So I don't gain anything. It looks more general, but it is in fact not. It's just that it's more convenient because I want to use the theorem volumes of line bundles, and then it's much more convenient to formulate it like this. So then I have then the following main lemma, which is then a refinement of this p factor I got with the implicit function theorem. So so maybe I should write it. Maybe I should still. I don't need this. Maybe this is much nicer than blackboard. So, well, how can I this one? Yeah, because I've already proven this theorem now, so I can reuse this. So I will state this main lemma, and then I will lift it back. So. So when I introduced this invariance, then this minimal model problem was not really completed. You have this problem with 4 orders. Maybe it had just appeared with Hake and McKernan, but now there's papers, so it's easier to find references. So introduce an invariant which is very hard to compute. And if you want to compute it, you have to use a minimal model program. And I can compute it for cubic hypersurfaces, so, but all for quartic threefold, I didn't have the energy. But maybe now, after these lectures, I will start to compute these invariants again. But, So let me state this main lemma here. I mean, my goal is I mean, I'm in the context of analytic number series, so if I can just improve an exponent by 0.001, even if I have a nice argument with my model program, I mean, I'm not that motivated, so I want to really to gain something to make effort here. So, but in some cases, you can get some good results. So let then here x of p of nq be as before, and I have then here x tilde, and I have then here y belonging to xp, fp, be as before. I mean, it has been the same the whole lecture, so this is still smooth. Non-singular y. And then I have this here Hilbert function, but now I will shift a bit, so I will define this at a0 of x, ox of k. But this is the same thing if k is sufficiently big. I mean, so this is not it's no difference. And then I will also have then here, I will also then have as before, p1 up to phk will then here belong to x tilde of set of y. So I will only consider now the p-adic factors here. So the size will not play any role, so I will just, and I will then also have global sections S1 up to then here is h of k, which will then lie in a0 of x tilde of O of k. And I will also then here have here an extra point. I will also have then here x belonging then to, because I will blow up a rational point in this class. So this could be one of those. So I can let then x q then reduce to this will then lie in x set y. So I take one additional integral point, but I will regard it as a rational point only. It could be one of those p1. I just pick one. What I plan to do afterwards is I will blow up. So I will define invariant, where I will blow up any point, a rational point representing this congruence class here. So then this determinant of Si of pi of j, where this have determinant of the same size, is divisible by, so now it's a better invariant here, divisible by p of ek for then, so here is now the definition of this e of k, so it's quite simple. There is no binary coefficients or anything. It's just the sum of k goes from 1 to infinity, and then I just take the dimension of the kernel of this map from H0. Where is the eraser? Can you tell me where the eraser is? I can't see it. Ah, there. Okay. So I look at this local behavior here, the multiplicity at this point x, etc., ox of k. And then there is, of course, a map here to a0 x of ox of k. So I multiply, I look at the local behavior of that, tensored with o x of x, modulo then the maximal ideal here. So it has support only in one point here, m x of x. And then what I have to, I have k, maybe k is not so good. I want m because I have k here, so it should be L then. L. So I look then at those global sections which vanish at a certain multiplicity at this given point x, which I choose, arbitrary point in this congruence class. So this is my new invariant. And for yes. So in particular, then, the determinant then, this is of course bounded below from the dimension here minus the dimension of this quotient of this ideal, so this quotient ring. So in particular then you get that the determinant of M is divisible by so I have then here j of k. It will actually the same expression as before. So it's a sum from j goes to 1 to infinity, and then I have them here maximum of 0 and the hk minus the sum. So this will just then be the sum of the dimension of those rings, and this is the same expression as I had before then. J goes from 1 to L. Oh, okay, I had L here. And I had then here something like R plus J minus 1 minus J. So, so I can recover the previous result. So I can estimate then this from below by I just take this dimension minus this dimension here. But this map doesn't have to be surjective. So why should it be surjective in general? So by using the fact that it's not always surjective, I can hope for something better than the previous result by using then studying this invariant here, E of k. And I can't prove this using the p-adic implicit function theorem, but I discovered a long time ago that one could prove the previous result without using the p-adic implicit function theorem. You just use some commutative algebra. You could still eliminate terms or so. So it's not much harder than the previous proof of the previous result. So so the interest now is then to try to and there is a difference because this is now a global invariant. So you need some, it has to do with this Hardy constant and so on. So you need information here about the global geometry. So so let me just, yeah, I will not. What time is it, by the way? Okay, fine. So first, maybe I should. Oh, maybe I take it down. I should. Interpretation here of the statement first here, because the statement is not absolutely clear because it's not functions anymore. So what do I mean here? I take the determinant of these sections here. So I have this expression here. So maybe I should make clear what I mean by the statement. Why? What do I mean that this is divisible by p here? So interpretation then. Of the result. Interpretation, of course, I think it's clear for almost all of you immediately. I mean, I think I have only experts in the room here. So anyway, let me explain it. So, so let then here L of I then be the restrictions of this sheaf. This is a sheaf, and I just restrict it to this pi. So then, of course, these are just invertible sheaves over spec of z. So then L1, LH of k are invertible sheaves, line bundles, as Suli said, invertible sheaves on spec of z. And then you have that this this determinant of Si of P of j is then a global, is thus a global section of this tensor product here up to L h of k. Global section then S of the statement means the assertion means that simply there exists another global section T on this spec of A0 of set of L such that P of E of k divides times T divides is equal to S. I think that was clear, but I just there's no divisibility between numbers or anything, so maybe I should still make precise what I mean. So, of course, you can then switch to polynomials if you want, and so on. So, so this is what this statement says. So now I would then like to understand this invariant here, A of k, and the best way to do that is to blow up. So this is a way to study multiplicity, because then you look then at the devices occurring, then this corresponds to the multiplicity of then the exceptional divisor in the blow up of corresponding global sections then here. So let me then here make this. I move this main lemma here, so instead I'll put a remark here. So let then here pi, did I call it pi, x1 to x be the blow up, x at x, and E be the exceptional divisor, and E be the exceptional divisor here. So let here also I then be the OX be the ideal sheaf, be the ideal sheaf of E in X of 1. So it's then an invertible subsheaf of O of X. So then there exists, of course, it's very elementary. Then there exists natural, I mean, just by this contravariant functoriality, a natural commutative diagram. So my goal is just to reformulate this invariant, to have it nicer, just depending on devices on the blow up. It's completely standard, so sure everyone here in the room could have done the same thing. So you have in here OX of k goes then here to H0 or X, and then I have OX of k tensorized then with OX modulo this multiplicities here. So this has then support in a point, and then I move it back then here to H0 x1, and then I have then here OX x of k, x1 of k now, when I turn it back, and then I have then a tensor OX1, but then I get this ideal sheaf instead, so it will then be I of L of x1. So this is then this will be isomorphic here, and then I will have here. In fact, I only need that it's injective, so I don't, since I will only be interested in the kernel here. So A0 of, and here I will, this will be isomorphic to x1, and I will then have P upper star of OX of k. So I will now replace this kernel here by this kernel here. And then I can interpret this invariant as a sum of global dimension of invertible sheaves of the blow up. So where then the kernel below equals then so I the dimension of A0, I write it with small a0 as usual. So this is then H0 of y, and then I have then here P star upper star OXK times IK here. So this this exponent and here EK, it's a sum of such finite dimensional vector spaces, and we will see in a moment that this will almost all of them will be 0. So when K is sufficiently big, I mean there will be no global sections here. It will be a finite sum. So what we get is then the following, that, or maybe I write it upstairs here. So can you start? Yeah, okay. So what I get then here is now that the assertion is now that this A of K can now be interpreted as a sum. L goes from 1 to infinity of H0 of this x1 of P upper star of O of x tensor then is I of L. So this is the expression I will have to. And of course, my end goal is to use Riemann-Roch in a certain way, asymptotically, but I will not use it only for ample devices. And at the end of his life, Zariski, he wrote papers on that, on surfaces, where he solved the asymptotic Riemann-Roch problem for non-ample devices. And this is also related then to this theory of volumes of line bundles, which are, for instance, exposed very well in Lazarsfeld's book. So I will now use well-known material you can find in Lazarsfeld's book. But I think it's more convenient, instead of writing all those sheaves, I will just represent them by devices. So I will use divisor notation. So suddenly we have an interesting geometrical problem. This is a purely geometrical problem. It has nothing to do with arithmetic, but it has some arithmetic relevance. I can go to Q or C even, there's no difference, so I will do that as well. I will look at every group, so over the algebraic closure. So I will then use the following equation. H will now be a hyperplane section. H belonging to be viewed as a Cartier divisor. So when I say divisor, I mean I could think about Weil divisor, but what I really mean is a Cartier divisor. So this is then the hyperplane section divisor, hyperplane section device of then x of p of n. And then I have then here that h1 is then equal to the inverse image of this. It's then a divisor on x1, and so this means then that so we have then that h0 of k h1 minus L of A. You can take that as a definition if you want. Is then a0 of pi upper star of OX of k tensor I of L here. But I prefer to write it in this way here. So so we are interested studying, and so we are studying the sum of all those H0 k H1 minus L of E, where L goes then from 1 to infinity. So we do this k then for all k. In principle, when k goes to infinity, if you want, when we are interested in the asymptotically behavior. We just want to show if k is sufficiently big, approximation or with certain properties. So, okay. Anyway, I want to study this some of these dimensions here, and then I need some definition here, which is related then to this work of Zariski, which is now studied by many people the last 10 years. So, when Lazarsfeld wrote his book, he said he was a bit complaining. People were not so interested in volumes of line bundles, but now I think there have been a lot of people using that, so it's expanding. So this book appeared, I think 2004. I mean, before all this minimal model program exploded in higher dimensions. So, but it still contains a lot of interesting material. Lazarsfeld, I think he spells like that. Positive algebraic geometry or something. 10, 12 years ago, maybe 15 years ago. So for then d dividing divisor of x1. So let then here the volume of d be the lim sup of when m goes to infinity of the dimension a0 of x1 of md divided then by mr divided by r faculty here. When this is ample, then this is just an intersection number then by the rock. So the interest here is when this is non-ample. And all the improvement of this easier bound I had before has to do with the fact that when the pseudo-effective cone is bigger than the ample cone, than the Neff cone. So I'm interested in the case where I cannot use Riemann-Roch theorem, when it's not ample, but when it's pseudo-effective and when it's big. So let me then make a number of remarks. I think this is well known to many people, but it depends what kind of background you have. So remark. So there will be no arithmetic now for the rest of my talk. It will be just geometry. But I mean, my motivation is purely arithmetic and even analytic number theoretic. So the volume of D is a geometric invariant. So we may work over Q. So we may work over Q bar or C or. So I will not make any specification that we are over Q or anything. So it's a geometric theory. So let then here and let then here, I think N1 of X then be the Néron-Severi group. So modulo numerical equivalence classes over then XQ then, XQ bar then. Now I want over X1 here. So it's over the yeah, here I wrote X, but okay, shall I write X1? It's a bit artificial. Yeah, okay, I do that. Because I intend to apply. So another remark here is that this is actually a limes here. Remark that you have that lim sup is actually equal to limes inferior here. So this is proven in Lazarsfeld's book. So you can you define it as a lim sup, but it's actually limes. Most of his book is written for in the case you have a non-singular variety. But I mean here I have very nice plane section and I blow up at a non-singular point. So I mean all the definitions extend. So anyway, I'm basically interested in the non-singular case because all those invariants here, they grow under specialization of the variety. So you actually only have to consider generic varieties and blow up at generic points because things could just get better when you specialize. So the worst case is a generic case. And so to say, usually in a family, if you have a Hilbert, component of the Hilbert scheme, parameterizing varieties, your generic fiber is usually smooth in the example I'm considering. So the difference between Lazarsfeld's book and what I need is very, very minor. So I also have then the following, say this was in the first remark, or this was one remark. So I have then here some other remark that if D is ample, then I have that the volume of D is now equal to the intersection number dr. So let's say then that it's smooth, too, but it should be defined anyway. Dr by Riemann-Roch. So this is the easy case. But if it were just as easy as that I just had ample devices, I would not get an improvement of the previous theorem. So the whole subtlety comes from the existence of non-ample devices. So also if you know the definition of big, so this is more or less by definition that the volume is positive if and only if D is big. And you have also here that the volume of M of D is equal to M of R times the volume of D. So there exists obvious extensions of this volume function, of this volume to Q devices. And in fact, one can prove that there exists a unique continuous function on R devices because it was a bit like we had before in this other function, the weight function. There's a unique continuous extension to R devices. So it depends only on the numeric equivalence class. So volume depends only on the equivalence class. Let's write that. So volume D depends only on n at x on the Néron-Savary group. So we have the following proposition. Then I think it's proved in Lazarsfeld's book. Otherwise, it's in his papers. So there exists a unique continuous extension of this volume function to the Néron-Savary group of x1 tensorized with R. So this is then a finite dimensional vector space, and this is then zero outside a bounded region. So in general, this can be quite wild. So it's continuous, but otherwise it doesn't have to be piecewise polynomial, I think, in general, this function. But for Banach varieties, and when everything is very nice, if you have the anticanonical, if you start with the anticanonical embedding, then you have only piecewise polynomial. So here then comes my invariant, so which I introduced in 2006. 2006 at MSRI talk. So I define then the following integral, then Ix of x is then the integral then here from 0 to infinity. I take then here the volume of h1 minus lambda e of d lambda. Let me just notice then that these sections, they cannot have, this hyperlength, they cannot have multiplicity higher than the degree of the variety, so that this is actually equal to corresponding degree from 0 to d here. So d was a degree of x. So it's a finite integral. I mean, this is so, yeah, so, or maybe I write it like this, that remark that this volume of h minus 1 minus lambda e is equal to 0 if lambda is bigger than d. So it's only a finite integral, but it could still be quite wild if you say have a variety of general type or so. So anyway, I can't compute it. It's very hard to compute. So except usually for Fano varieties. So the reason I introduce it is that this is kind of an approximation to this sum. So if I want to understand the asymptotic behavior of this sum, then it leads to the study of the integral here. So this invariant, no one has seen anything similar in 2006. So suddenly then, in 2014, it's appeared then in a Inversiones paper by McKinnon and Roth on Diophantine approximation. So the study on how well a point on variety could be approximated by rational points. So let me quote their paper. So remark that this I x of x was reintroduced by McKinnon-Roth. There are two Roths. So they were interested in Roth's theorem, but it was a field prize. This is not a Fields Medal winner, so this is a modern paper. But so just to make it even more complicated, there are two Roths here. So he emphasizes himself that he is not a famous Roth. He writes that more or less in the paper. So I don't think I mean, he might be famous as well after this paper, but still, I mean, Roth theorem is a landmark in mathematics. So, but there are many generalizations of Roth theorem, and here is one nice statement. So, to state it, their generalization, they use actually this invariant here. And I just met, I think, a student of Manuel Per who's finishing a thesis in August. So you may have further information about this invariant there. And perhaps for me more interesting, Donaldson's this program with K-stability. Then there is there are two roots, but there are also two Fujitas. So the Fujita now is not a known Fujita. He's very young, but I think he will coming star. So I write here Kento Fujita. So he is a student of Oka, who's a student of Mori, so they all are in the same gang in Kyoto and the minimal model program. In the theory of K-stability related to Kähler-Einstein matrix, and he does it in great generality. I mean, he knows everything about this Mori program in high dimension, but I did not really find anything that was useful for the problem I'm interested in to compute invariant, say, for varieties. But there are many other problems he solved brilliantly using this invariant. So he related to something called Ding stability, which was a purely analytic invariant that was used in the theory of Kähler-Einstein matrix. So I think his papers are very interesting, and I discussed him, but I think we are not. So this was in 2000. So I don't think I can use anything of his papers, but I strongly recommend you to look at them. They are very interesting. So why is the motivation then for introducing? Well, I have to explain this is linked to this invariant E of K. Motivation. I just make here some heuristics here, so that I have then here that E of K, which is then equal to the sum of all those L of goes from 1 to infinity of H0 of K H1 minus L of E is then approximately. So if now you say that K is large, if you now remember the definition of volumes, then this should be equal to the sum where L goes to from 1 to infinity of, and then you will have then here Kr times R faculty. This was used when we defined volumes, and then we'll have then here the volume of H1 minus L divided by K of E. And this in its turn, you can approximate this by this integral here. So this will be approximately isomorphic to Kr plus 1 times R faculty times I. So now there is still a problem that there is an error term here. So this is just an approximation. So then, in order to control the error terms, I mean, I could always do it. In all cases, I could compute the integral. So that was not to have an issue. But I mean, I don't know how to control the error term without using form of minimal program, or one or another. So maybe I will, in a moment, add an extra hypothesis that it's a finer variety. So let me just then say that what I want to have, it's quite clear that this integral should be relevant here. But in favorable cases, like affine varieties and H anti-canonical divisor, favorable cases are basically all where you can compute I, where you can use it. So then we have that this, shall I call it star, that E of K is equal then to Ix of X times Kr plus 1. I'm a bit tired now. Maybe there is some R faculty here, but that could be sorted out, so I'm a bit tired. So I have O of K of R. Maybe there's an R faculty here, but in principle that should be correct. So then I have then here the following theorem here is now that this star actually holds very uniformly here if X is Fano, and H is the anti-canonical divisor here. So proof, what you do is then that you use a minimal model program, and especially you could, I think, use this original paper of these 4 authors with, I don't remember, among them there were Hakon McKernan, but I think it's better to use a theorem of the paper by Kalagirus. I'm not very good at such names. And then it's Kirunia, I think it's in Frankfurt. So I think it's a Hungarian name, so Lasic, that I think I can pronounce it correctly. So, okay, so these are well-known geometers. So the point is now that the following, that there exist rational numbers, 0 smaller than P1 to Q1, etc., to Pk of Q of K, that this I is equal to then the integral. So if I call this P0 then, P0 my Q0, so I have then a Pi modulo Q of I modulo Pi plus 1, Ki plus 1, so that this I is the sum of those. So these are only finitely many. And then I have then these volume functions, a volume of H1 minus lambda E of d lambda. And the point is then that on each of these, this is now an intersection number here on some contraction, on a contraction, birational contraction. It's not always defined everywhere, on a birational contraction. So this function is piecewise polynomial, and you have only finite many pieces, and on each piece you use a Riemann-Roch because you can express this as an ample, as an intersection number of an ample divisor. This is not ample except on the first part, but it's equal to the volume of an ample divisor on this birational contraction. So this means that you can compute it using intersection theory, and you can control then the error term. So, to control the error terms here, I think I really need some form of the minimal model program, but that can be achieved. And an interesting that this is actually rational as well. You get that this integral is rational. If you looked at this theorem I wrote on the blackboard, it was quite horrible with all these roots and everything. But if you write it in this form for final variety, actually you can always replace this exponent by a better rational exponent. And all this follows from the minimal model program. So it's all beautiful and fantastic. The problem is that the numerical improvements are on the star order 0.001 or so. Okay, you replace an irrational number by rational number on these estimates, but I mean, the gains are not enormous. So how much work should you do just to have 0.001? I mean, it has to be a big problem. So let me just then, I think I have to, yeah, I have, say that in the case of cubic, yeah, maybe I should still state then the analog of this main theorem here, which I stated in the beginning then here. So now I can replace this Heath-Brown exponent by an exponent which is better. So to be safe, let's state it for final varieties and canonical divisor. I think you don't need it anti-canonical. You can do it for other varieties. So let me unstake theorem. So let then here x of p of n be an anti-canonically embedded Fano variety, embedded Fano variety. So this means that this star holds, and let then here P then. So then let's see. Then if P is bigger than B d degree divided by this integral plus epsilon, then we have the same statement as before for n, what was it? It was x q b y for non-singular then y modulo then y of fp here. No, x tilde p. So it's exactly the same theorem as I stated in the beginning. It's just that you have d of I instead. You can show that d of I is always bounded from above by this exponent, this strange root exponent of Heath-Brown. So in some sense, if you can just solve this, control this error term here, then it's always, I mean, you have always a better theorem. But I only know how to control it, I mean, say for Fano varieties or so. But this is already very interesting because there are many interesting Fano varieties. So let me just say that I have been able to compute this for generic, for quadric, for instance. So for quadrics, it's easy to compute this. So I will finish in, I have still 5 minutes, so I will finish in time. So examples. So for then generic hypersurfaces of then surfaces x and generic then point x of x. So there is always a generic hypersurface. I mean, I can make transcendental field extensions, and so there is a Very interesting invariant to compute this for all for generic hypersurfs. So then you have that d of I, so that for if d is equal to 2 implies that this d of I is equal to 1. And this is now smaller than r plus 1 divided by r times the 2, 1r. And if d is equal to 3 and the dimension is at least 2, then I can compute that this is equal to 2r plus 2 divided by 2r plus 3, which is smaller than r plus 1 or r's root of 3. So you get the improvements, but for surfaces still they are quite small. So let me just then end with what is now the best result known so far on these Manin conjectures for general cubic surfaces. So, and this improvement is obtained using these volume functions for cubic surfaces. I should say for surfaces it's not hard to compute this because there is something called Zariski decomposition of each divisor. So you can directly express them as intersection number in an easier way. But I still like to do this by rational transformations because in order to generalize it, so you have to do that. I mean, there is no good analog of Zariski decomposition in high dimensions. But let me just then end with the state this result for cubic surface, which is one thing which motivates me here. So I have to stop. So I think that's a good way to stop. So corollary of all this. So let x of p of q 3 be a non-singular. I think it works for the singular case as well, but let me. No, I don't think I need it. Be an integral. Yeah, but I want to have the 27 lines. Okay, I have to remove the lines. But let me just since I'm short of time. So. Non-singular cubic surface, and then u be equal to x, where now I remove the union of the 27 lines. And then, of course, I can count the points on this open subset, and then I have that the number of point of heights at most b is then equal to O, and this is a uniform result. It depends only on epsilon then. B root of 3 plus epsilon. I proved that some years ago. And recently, I think in a paper in this Bond proceedings in a book, I improved this to O of E times B 12 over 7 plus epsilon. So this is then obtained by the p-adic implicit function theorem. So this is obtained by using this integral, this volume integral, volume, etc. Now you can compare this to, because it's quite representative. So what are then the numerical values here? So the numerical values here are here 1.732, and you have here 1.714. So this is quite typical. I should say here that it's not enough to use this p-adic determinant method I've explained, because if you use it in the form explained here, you still only get that it's covered by that many curves, and that it's covered by that many curves. So there are other ingredients which are deeper than anything I have explained here. There's something called the global determinant method that I use at all p at the same time. And this is much more awkward because here you can just divide everything in p-adic boxes. If you look at all p's at the same time, there is no such division. So I use a more a deeper version of the determinant method than I have explained in these talks. But in order to understand that, you first have to learn the ordinary p-adic determinant method. So I would need another week to explain the global determinant method. So I think it's really I should stop here. So I thank you for your patience.